Victoria's goldfields produced more than 2,400 tonnes of gold. They transformed a remote British colony into one of the richest places on Earth, triggered one of the largest gold rushes in history, and helped shape modern Australia. Most geologists will tell you that this gold was formed by mountain building, deep crustal faults, and fault systems that developed hundreds of millions of years ago. But what if there was another player in the story? A player so large that, if it exists, it may be the biggest impact structure on Earth. Buried beneath southeastern Australia is a mysterious circular feature more than 500 kilometres wide. Few people have heard of it. Fewer still realise that some scientists believe it may represent the deeply eroded remains of a colossal asteroid impact. And if they are right, a remarkable question emerges. Could an asteroid have helped create Victoria's goldfields? At first glance, the idea sounds absurd. Goldfields and asteroids seem to belong in completely different geological worlds. One involves quartz veins, hydrothermal fluids, and mountain building. The other involves explosions, shockwaves, and planetary destruction. Yet the deeper you look, the more intriguing the question becomes. To understand why, we need to travel back more than 450 million years. At that time, Victoria looked nothing like it does today. There were no forests, no grasslands, no goldfields, no towns, and no Great Dividing Range. Instead, much of southeastern Australia lay beneath an ancient ocean at the edge of Gondwana. Across this submerged landscape, vast underwater avalanches repeatedly swept sediment into deep marine basins. Layer after layer of mud, silt, and sand accumulated on the seafloor. Over millions of years, these deposits built up into enormous thicknesses of sediment. Today, we know these rocks as the Ordovician turbidites. They formed a foundation of Victoria's goldfields. Bendigo, Ballarat, Castlemaine, Fosterville. Most of the gold produced from these famous districts came from quartz reefs hosted within Ordovician sedimentary rocks. The rocks were already there long before the gold arrived, and that detail is important, because the gold itself did not form until much later. During the Silurian and Devonian periods, southeastern Australia became caught up in a series of tectonic events associated with the growth of the Lachlan Orogen. The crust was compressed, faults developed, sedimentary rocks were folded into giant anticlines and synclines, granites intruded at depth, hot fluids circulated through fractures, and somewhere within those fluids travelled gold. As pressure and temperature changed, gold precipitated from solution and became trapped within quartz veins. Those veins would eventually become some of the richest gold deposits ever discovered. That is the traditional explanation, and it remains the accepted explanation today. So where does an asteroid come into the story? The answer begins beneath southern New South Wales. Buried beneath the Murray Basin lies the Deniliquin Structure, and this is where the mystery becomes even stranger. Unlike famous impact craters elsewhere in the world, nobody can actually see it. The structure sits beneath hundreds of metres of younger Murray Basin sediments. There are no exposed crater walls, no visible central uplift, no obvious impact breccias, and no circular mountain range marking its outline on the landscape. Standing above it today, you would never know it exists. Instead, scientists are attempting to reconstruct a giant geological feature hidden beneath the basin using magnetic surveys, gravity data, seismic imaging, and a relatively small number of drill holes that have penetrated the underlying basement rocks. The structure appears only when viewed through geophysical data. Magnetic surveys reveal a giant circular pattern. Gravity data outlines broad concentric rings. Seismic studies suggest the crust beneath the feature differs from surrounding regions. Even the mantle appears unusual, rising closer to the surface beneath the centre of the structure. Together, these datasets reveal a feature exceeding 500 kilometres in diameter. If that interpretation is correct, the Deniloquin Structure would not merely be Australia's largest impact crater, it would rival or exceed the largest known impact structures on Earth. That immediately raises an obvious question. What happens when an asteroid creates a crater more than 500 kilometres across? The answer is simple. It changes everything. Large impacts do more than excavate holes in the ground. They fundamentally alter the crust. Shockwaves travel hundreds of kilometres. Rock masses fracture. Deep faults develop. Entire regions become structurally weakened. And those weaknesses can persist for hundreds of millions of years. This is where the connection to Victoria's goldfields becomes interesting. Gold deposits are controlled by structure. Hydrothermal fluids need pathways. They need faults and fractures. They need zones of weakness that allow them to move upward through the crust. Without those pathways, the fluids remain trapped deep underground. The question therefore is not whether an asteroid created the gold. The gold already existed within the Earth's crust. The question is whether an asteroid helped create the plumbing system that later concentrated the gold into mineable deposits. The idea is not entirely without precedent. Some of the world's most important mineral deposits are associated with impact structures. The Sudbury Basin in Canada is perhaps the most famous example. Created by a giant impact approximately 1.8 billion years ago, Sudbury contains world-class nickel, copper and platinum group element deposits. Elsewhere, impact-generated hydrothermal systems have been linked to mineralization processes. Large impacts can fracture the crust, mobilize fluids, and create favourable conditions for ore formation. The question is whether something similar could have happened in southeastern Australia. At first glance, the timing appears promising. The proposed age of the Deniliquin structure overlaps the period during which the Ordovician sediments of Victoria were accumulating beneath the sea. If a giant impact occurred during this time, the surrounding crust would have experienced immense stress. Regional fracture networks could have developed. Deep crustal weaknesses could have formed. These weaknesses might then have been inherited by later tectonic events. When mountain building began tens of millions of years later, the crust would not have started from a blank slate. Instead, pre-existing structures could have influenced how stress was distributed throughout the region. Faults may have preferentially reactivated, granites may have exploited existing weaknesses, and hydrothermal fluids may have followed ancient pathways. Gold-bearing quartz reefs may ultimately have formed along structures whose origins stretched back into deep geological time. It is a fascinating possibility, yet there is a major problem. There is currently no direct evidence linking the Deniliquin structure to Victoria's goldfields. No study has demonstrated that the major gold-bearing faults originated during the proposed impact event. No study has shown that mineralization was controlled by impact-generated structures. No study has identified a direct relationship between the two. At present, the connection remains entirely speculative. And there is an even bigger problem. Nobody has conclusively proven that the Deniliquin structure is an impact crater. This is where the story takes an unexpected turn. Despite the impressive geophysical evidence, researchers have yet to discover the smoking gun indicators that normally confirm an impact origin. There are no confirmed shocked quartz, no shadow cones, no impact melt sheets, and no definitive impact breccias. The structure looks like an impact. It behaves like an impact. But the direct evidence remains elusive. Supporters of the impact hypothesis point out that this may not be surprising. Much of the proposed structure remains buried beneath hundreds of meters of Murray Basin sediments. Unlike exposed impact structures where geologists can walk across crater rims and directly sample impact rocks, Deniloquin is largely hidden underground. The basement rocks are known primarily from scattered drill holes. It is entirely possible that the most important rocks have never been sampled. The very thing that may have helped preserve the structure for hundreds of millions of years, the thick blanket of Murray Basin sediments, also makes it extraordinarily difficult to prove what lies beneath. Perhaps the shocked rocks are still there, perhaps the impact melt still exists, and perhaps the critical evidence simply lies between existing drill holes. That possibility cannot be ruled out. But critics raise an important counter-argument. Even if the crater itself remains buried, a 500-kilometre impact should have left evidence beyond the crater. And this may be the most serious challenge facing the impact hypothesis. If the impact occurred while southeastern Australia was underwater, enormous tsunamis would have swept through the surrounding seas. Huge quantities of ejecta would have been blasted into the atmosphere. Shockwaves would have travelled across the sea floor. The larger the impact, the larger the geological footprint. Some of that evidence should still exist. And this brings us back to Victoria. The Ordovician rocks that host the state's famous goldfields have been studied for more than a century. Thousands of kilometres of drill core have been examined. Countless mine workings have exposed the subsurface. Generations of geologists have mapped the stratigraphy and structures. Yet no confirmed ejecta layer has been linked to Deniloquin. No unmistakable impact horizon has emerged, and no definitive tsunami deposit has ever been identified. That absence is difficult to ignore, because unlike the crater itself, ejecta deposits do not need to survive within the impact structure. They can be preserved hundreds or even thousands of kilometres away. In some cases, ejecta layers survive even when the crater that produced them has largely vanished. If Deniloquin really was a gigantic marine impact, some researchers argue that evidence may still be waiting to be discovered within the Ordovician sedimentary record. And that possibility opens a remarkable avenue of investigation. What if the proof of Australia's largest impact structure is hiding within the very rocks that host Victoria's gold? What if the answer is sitting inside an overlooked sedimentary layer somewhere beneath Bendigo, Ballarat, Castlemaine or Stawell? Or perhaps the opposite is true. Perhaps the absence of ejecta, tsunami deposits, and shocked minerals is telling us something important. Perhaps the impact never happened. That is what makes the Deniliquin structure such a fascinating geological mystery. If it is an impact crater, It may have altered the evolution of the crust across southeastern Australia and potentially influenced the geological architecture of one of the richest gold provinces on Earth. If it is not an impact crater, then one of the largest circular geological features in Australia still awaits an explanation. Either possibility would be extraordinary. Could an asteroid have created Victoria's Goldfields? Probably not directly. Could it have helped shape the crust that later concentrated gold into the quartz reefs of Bendigo, Ballarat, Castlemaine, Stawell and Fosterville? Possibly. But before that question can be answered, geologists must solve an even bigger mystery. Buried beneath hundreds of meters of Murray Basin sediments lies a giant circular structure that may be one of the largest impact scars on Earth. Or it may be something else entirely. Until the missing evidence is found, nobody knows which answer is correct. Hope you found this as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.